Section 2. Understanding Container, Podman, and Kubernetes. Part 1. Container. In this section, you'll learn about containers, the core technology of the container platform. Containers are large shipping containers used to transport cargo. Just as different types and sizes of things can be packed into a container to make them easier to transport, container technology is simply a way to package different program elements and put them into a single container. In other words, a container is an OS that bundles and packages the minimum elements for a program to function, and is a kind of virtual machine that enables independent deployment and execution. Before container technology became popular, application deployment evolved through several phases. In the traditional deployment era, applications were installed and used on physical servers. There was no way to define resource limits for multiple applications on a single physical server, which led to resource allocation issues. For example, if you ran multiple applications on a single physical server, you might have an instance of an application that took up all of the resources, resulting in poor performance for other applications. The solution was to run each application on multiple different physical servers, but this was not scalable and that resources were underutilized, making it expensive to maintain many physical servers. As a solution, virtualization was introduced, which is a way to allow multiple virtual machines to run on the CPU of a single physical server. Virtualization allows you to isolate applications between virtual servers and provides a level of security because the information in an application is not freely accessible to other applications. It also allows you to utilize resources more efficiently than on a physical server and provides better scalability because you can easily add or update applications and reduce hardware costs. Virtualization allows you to turn a set of physical resources into a cluster of disposable virtual machines, each of which is a complete machine running all of its components, including its own operating system, on virtualized hardware. Finally, containers are similar to virtual machines, but they share an operating system between applications by relaxing isolation properties. Because of this, containers are considered lightweight, and like virtual machines, they have their own file system, CPU occupancy, memory, process space, etc. Also, they can be ported to any cloud or operating system distribution, because they have broken the dependency on the underlying infrastructure. There are two main types of virtualization technologies: hypervisors and containers. The first, hypervisor-based virtualization, is a technology that runs a virtualization software, a hypervisor, on top of hardware, a single physical server, to create and run multiple guest OSs. Containers, on the other hand, are a technology that runs multiple applications in independent containers on top of a single host OS, using container management software. Let's compare the difference between a virtual machine and a container with the help of an illustration from the textbook. A virtual machine is a monolithic system that allows multiple operating systems to run simultaneously on a single physical server. It has a virtualization layer in the middle, and each OS is configured to run applications on top of it, which means that it takes a long time to run applications and is burdensome. Containers allow you to run multiple independent containers on a single operating system. Each container only needs to configure a minimal execution environment for the application to run, which has the advantages of being small, lightweight, and fast to run. They also have the advantage of running multiple containers simultaneously on a single kernel, and the small size of applications running in isolation between containers makes them highly scalable and easy to deploy. Because of these advantages, containers are becoming more popular than virtual machines. Let's take a look at the features of containers. First, compared to using virtual machine images, creating container images is easier and more efficient, allowing you to create and deploy applications with agility. Container images can be built and deployed reliably and periodically, and can be rolled back correctly and efficiently, enabling continuous development, integration, and deployment. by creating application container images at build release time, rather than deployment time. Applications are decoupled from infrastructure, and you can see the health and other signals of your applications, rather than being limited to operating system level information and metrics. It runs the same on your laptop as it does in the cloud, ensuring consistency across development, testing, and production environments. It's portable across clouds and operating system distributions, so it runs on all major public clouds and anywhere. And because it's application-centric, it takes virtualization to the next level, with applications using logical resources by running the operating system on virtual hardware. Applications can be deployed and managed as free microservices, resources are isolated, application performance is predictable, and resource usage is highly efficient and dense. Next, we'll discuss container management and execution tools. A container engine is software that provides API or CLI tools for managing containers. Examples of container engines include Docker Engine, Red Hat's Podman, and Rocket Company's Arcade. The container engine takes user input, fetches container images, creates metadata that describes how to run the container, and then passes that information to the container runtime. The container runtime is the tool that takes the root file system and metadata and runs the container. The most common runtime is OCI compliant runc. Other common runtimes like Containerd and CRIO actually rely on runc. Let's look at the architecture of an application based on container technology with the help of an illustration from the textbook. The figure depicts an OCI compliant container app lifecycle workflow. The environment required for containers to operate and run is an operating system, such as Linux or Windows, on top of an infrastructure, such as hardware, or the cloud. On top of that operating system, libraries that automate the art of creating containers and a container runtime, which is the platform on which those libraries can run, are installed. Container runtimes that comply with the OCI standard include Containerd and runc, which isolate resources and create and run isolated containers. They also provide security, volume, networking, secrets, orchestration. You need a container engine that does things like distributed state. These two components, the runtime and the engine, are needed to run a container, and the container engine passes the user's input to the container runtime, which downloads the images needed for the container and runs the container configuration file to get the container working. The container app lifecycle workflow provides integrated lifecycle management, including content trust and verification, private image registry, secure access and user management, application and cluster management, image security discovery, and continuous monitoring and policy management. Part 2. Podman. Podman is a container engine that lets you run, manage, and deploy containers and container images. Podman stands for Pod Manager Tool, and it's a daemonless engine that doesn't have daemons, which are background processes that run for a long time to respond to service requests. Podman is characterized by its ability to run routeless containers and isolate resources for pods, creating a more accessible container environment while reducing security risks. It is also compliant with the Open Container Initiative and is nearly identical to Docker CLI commands. Finally, Podman deploys a RESTful API to manage containers. Docker, often compared to Podman, is a tool with similar but distinctly different properties. Docker consists of Docker Engine for building and containerizing applications, Docker Registry, and Docker Compose for deploying and serving container images, and Docker Machine, Docker Swarm, and more. Of these, Podman can be seen as similar to the Docker Engine, which is the core functionality of Docker. Docker Engine also has a Docker daemon to run containers and a command-based Docker client that users use to manage images and containers. Similarly, Podman has a container image for running containers and a command-based tool for working with the containers and the images run through it. More specifically, Docker gets images from the container registry and stores them in the image repository inside Docker. Images stored in the image repository can be used to run containers, and running containers can be built from images. Docker performs all of these tasks through the Docker daemon. So if something goes wrong with the daemon, it can affect all containers and images, and it can also affect controlling containers with commands. Podman, on the other hand, uses commands without a daemon to get an image from the container registry, store the image in the local image store on the Podman host, and run the container using that image. Because you're running containers directly through the Podman library, they don't affect each other, nor do they affect the commands you use to control them or manage their images. Podman's approach interacts directly with the image registry, container and image storage, and the Linux kernel through the runc container process. Podman doesn't require you to start or manage daemon processes like the Docker daemon, and the commands you're familiar with in Docker work the same in Podman. It stores containers and images in a different location than Docker, and Podman and Docker images are compatible. Part 3. Understanding Kubernetes. The K-PaaS container platform is based on Kubernetes. In this part, we will learn about Kubernetes. Kubernetes is a container orchestration system that makes it easy to deploy containers quickly and efficiently, and to continuously check and manage container health. In this context, orchestration refers to the automated management of computer systems, applications, and services. In other words, Kubernetes is a tool that automatically manages the health of your containers. These are some of the features of Kubernetes. First, because Kubernetes can expose containers using DNS names or using their own IP addresses, it can load balance and deploy network traffic to ensure that your deployments are reliable when container traffic is high. Second, Kubernetes allows you to automatically mount the storage system of your choice, and you can describe the desired state of your deployed containers with automated rollouts and rollbacks. Next, provide a Kubernetes cluster node that can be used to run containerized jobs. You tell Kubernetes how much CPU and memory each container needs, and Kubernetes fits the containers to the nodes to make the best use of resources. It also restarts and replaces failed containers with automated recovery. Finally, Kubernetes allows you to deploy and update secrets and application configurations without reconfiguring container images and without exposing secrets to the stack configuration. Next, we'll look at what a Kubernetes cluster is composed of. A Kubernetes cluster is a set of node machines running containerized applications. A cluster consists of one master node and one or more worker nodes. The master node is the machine that manages all the nodes inside, while the worker nodes are the machines that receive commands from the master and do the actual container creation and work. A Kubernetes cluster basically consists of one or more master nodes and three or more worker nodes, as illustrated in the textbook. As we saw earlier, it consists of a master that manages the entire cluster and worker nodes where containers are deployed. All commands call the master's API server, and the worker nodes communicate with the master to perform the necessary tasks. When you give a command to a specific node, the command does not go directly to the node, but rather you give the command to the master, and the master contacts the node and responds with the results. First, let's take a closer look at the components of a master node. First, the Kube API server can be thought of as the front end of the Kubernetes control plane. All communication in Kubernetes will be initiated through the Kube API server and will receive communication from kubectl. Next, the Kube controller manager is responsible for controlling each of the controllers that manage the pods. The third, the Kube scheduler, is responsible for allocating resources to the nodes that are available. And finally, etcd is the repository behind Kubernetes that holds all the detailed data within the cluster. A cloud control manager is a component that manages controllers by connecting them to cloud services. The worker node's kubelet is an agent that runs on every node and communicates with the master's Kube API server by running containers and performing continuous health checks. And the Kube proxy is a network proxy that runs on each node in the cluster, setting up and managing an internal virtual network. Next, let's look at the Container Runtime Interface, or CRI. When users make API requests to Kubernetes, they do so using an internal API from the master node to the worker nodes. Kubernetes CRI is the API that allows Kubernetes to use different container runtimes. CRI acts as a client when connecting with a runtime through a protocol called gPRC. RunC provides all the low-level functionality for containers, interacting with existing low-level Linux features like namespaces and control groups, and uses these features to create and run container processes. What tools are used to deploy Kubernetes? There are three main Kubernetes deployment tools that you'll see in the book. First, Podman is a management tool that makes it easy to install Kubernetes in a typical server cluster environment. Any common Linux server can be used, regardless of the infrastructure environment. Next, KaaPaaS is an automated provisioning system that allows you to quickly and easily install a Kubernetes cluster on AWS. Finally, KubeSpray is an open-source tool to flexibly and easily deploy and manage Kubernetes clusters through Ansible. Namespaces are a logical unit of separation within a Kubernetes cluster. The illustration in the book is a representation of a namespace where a Kubernetes cluster is divided into namespaces called Dev1, Dev2, and Dev3. Users of the Dev1 namespace can access and operate in the Dev1 namespace region of each machine, while users of the Dev2 namespace can access and operate in the Dev2 namespace region of each machine. In this way, namespaces are a logical separation of the cluster. The concepts of resources used in a Kubernetes deployment. First, namespace refers to the division of a physical cluster into logical units. Next, deployment is used for the deployment and management of the pods that need to run, while managing replica sets. Replica sets are responsible for maintaining and managing the number of pods. Pods are the smallest units that run on containers. Fifth, the service provides an IP address to allow access to pods inside the cluster from outside the cluster. 6. Volumes are part of a pod and are responsible for holding and maintaining data for containers. And volumes can be shared between containers within the same pod. We'll learn more about resources starting on the next page.